You're tuned into Vessel Performance Info's webinar with Danelec, Managing Quality of High-Frequency Vessel Performance Data. Our guest speaker is Conrad Gessler, Director of Ship Performance Product Management for Danelec. If you have any questions for Conrad, do leave them in the Q&A section and we'll get them answered for you after the presentation. Starting off the webinar is our founding editor of Digital Ship, Carl Jeffrey. Over to you, Carl.
So our topic today is managing the quality of high-frequency data from ships relating to vessel performance. So by high-frequency data, we mean data collected very often, such as once a second or once a minute. And the high-frequency data we gather relating to performance, that's usually propeller shaft torque or force, and the vessel speed and the fuel consumption. So we're talking about shaft power meters, speed logs, and fuel flow meters. And common reasons for problems with this data are interruptions in data transmission to the shore, sensors drifting out of calibration, and sensor faults such as fuel flow through a meter getting blocked. And if you've got bad quality data, then of course your vessel performance models might be wrong. So your performance decision making and voyage planning will be less effective, and you might be sending the wrong data for regulatory reporting. Our company presenting today, Danelec, provides services to work with high-frequency data on 15,000 ships. That's either as a supplier of its Kymer shaft power meters, or collecting and sending data to the cloud with its Danelec Collect solution, or providing voyage optimization and technical performance monitoring services. So Danelec see a lot of high-frequency data and they know how to work with it. Danelec also provide a software tool which can make you aware faster about problems with your data and perhaps improve its quality with filtering and automated outlier detection. Our speaker today is Conrad Gessler. He's Vice President Product at Danelec. He's joining us from Brooklyn in New York. Conrad has got a background in both digital technology and international strategy and security, so they must both be good for working with maritime technology. Conrad's going to give a talk of about 25 minutes, then we'll take your questions. You can put them in the Q&A box at any time, but we'll take them at the end. And I'd like to invite Conrad to start the talk.
Yeah, thank you so much, Carl, for that introduction. Appreciate that. And thank you, everybody, for tuning in. I'm really excited to share more about this topic, which we at Danelec think a lot about and experience every day. So if you just give me a minute, I will share my screen and pull up a few slides.
Yeah, it's good.
Great. So just to give you a high-level sense of what we will cover today, I'll start by giving you a brief introduction into Danelec and explain some of our history and our solutions. I'll then make a case for why high-frequency data is the path forward for the maritime industry, highlighting a few benefits of upgrading to that data granularity. I will expand on Carl's introduction about some of the common challenges that we see working with high-frequency data, using a few real examples from vessels in our data pool. And after that, I'll demo a module that Danelec has been building called Data Quality, which helps our clients not only detect poor quality data, but take a few actions to correct the data as well. After that, I'll tease some upcoming releases into that data quality module, give you a sense of how we're thinking about the problem and some of the future development. And then I'll close with a few key takeaways. And at that point, we'll open it back up, and I'm looking forward to your questions. So to start, let's just talk about Danelec at a glance. There are three core competencies of our business. One is maritime safety. We're a leading provider of voyage data recorders, VDRs, as they're commonly known. Another is data collection, which is actually collecting all the various high-frequency data from systems on the vessel and transmitting that to both other applications in the vessel and onshore via APIs. And as Carl mentioned, we're also, one of our core competencies is AI-based analytics. So that's things like monitoring the technical performance of the vessel, looking at speed loss, the condition of the engines with specific fuel rate, and also predicting voyage outcomes with our voyage optimization product. So together, these solutions help us both drive digitalization in the industry and help clients achieve net zero targets. On the right-hand side here, just a few high-level statistics about the business. We've been in the maritime industry for over 30 years, and we have an extensive network of partners, over 200 partners with combined 700 technicians, which can easily get onto vessels both to install our data logging equipment, the chef power meters that we offer, and provide any maintenance that's required. So quite a global reach to be able to get onto vessels and help install hardware. Across all of our products, we have an install base of 15,000 vessels, which is quite a good coverage when you're looking at the total size of the global merchant fleet. And this last number here, I think most interesting to this group today, is just the volume of data which we're collecting across our products. So last year alone, we collected over 1.5 trillion data points, high frequency data points. And so we do have a lot of experience of collecting this data, working with it, and actually leveraging it for analytics to help make decisions. As I mentioned, Danelec does have quite a broad product suite, but I wanted to highlight two of our offerings which are most relevant to the topic today. One of them is the vessel remote server, which you can see here on the left-hand side. That is our data logging solution that is also E27 cyber approved and allows us to collect various signals coming from the vessel, whether it's fuel flow, something from the IAS system, draft, speed logs, power meters. We can take all of that data, synchronize it with timestamps, and also easily transmit it over satellite connectivity to any onshore applications. The system does have local caching and edge computing to deal with outages as well. And currently, we have this installed on over 3,000 vessels. On the right-hand side, you'll see the Kima power meter. So Danelec acquired Kima in 2021, which is one of the premier technical performance companies in maritime, specializing in manufacturing shaft power meters and onboard performance software directly for the crew in the engine control room. So these are some of the leading torque meters that can measure, as I mentioned, torque and also thrust. We have an install base of around 7,000 of those units installed. And so combined, these product suites give us a really great inside look into both working with high frequency data, detecting outages, detecting challenges, and also importantly, correcting that for our users. Okay, so let's take a little step back and just talk about why high frequency data is the path forward for the industry. There are three big reasons which I'll highlight. The first here is pretty simple. You can't improve what you can't measure. So there are some use cases in our industry that require the higher frequency data in order to actually take any action and save fuel. I'll highlight two of them here. One of them you'll see is saving fuel with generator optimization. So what we mean here is looking at the actual real-time hotel load requirement on a vessel, and then looking at the configuration of the generators to see, is that the optimal configuration such that we're taking advantage of higher loads on less generators, thus reducing fuel consumption, compared to using multiple generators at much lower loads, which is less efficient. Over the sailing lifetime of a vessel, these sorts of small savings can add up. In some more extreme cases, we've seen larger vessels in our pool with the ability to save around 5 metric tons of consumption just by correctly configuring the generators and optimizing their usage. Now, this requires high frequency data because if you're just relying on one average point from a noon report, it's really hard to understand where there were inefficiencies throughout the day of how the generators were operated, and it's almost impossible to give that guidance directly to the crew. So this is one clear example where high frequency data is required. On the right-hand side, we have minimizing LNG consumption with boil-off gas optimization. This is a use case that is specialized for LNG carriers, and it's looking at the actual real-time pressure and temperature of the LNG cargo in the tanks and providing predictive insight into how to manage that over the course of the voyage to minimize LNG consumption and still hit commercial targets. The reason why this requires high frequency data is because it's almost impossible to build any usable model to model how the cargo changes over time and to prescribe any recommendations if you don't have that higher granularity data. This product can save up to 35 metric tons of fuel on laden voyages, let alone some of the savings that you could use to get that insight to negotiate with terminals and actually come in at higher pressures. So these are just two specific use cases that help us understand why high frequency data is really important to drive deeper fuel savings. The second reason why high frequency data is the path forward is another simple one, and that's just it delivers higher prediction accuracy. And when I say prediction accuracy, I mean our ability to train a model of the vessel that can predict how fast it will go or how much fuel it will consume in different weather patterns and sea states. That's really important because you need those models to squeeze out a fuel savings in your voyage planning. And as more and more ship operators are using this type of technology to optimize their voyages, it's going to be paramount to get the best data you have to keep up with those savings and remain at par with other operators. And on this slide, you'll see two kind of simple images, which I'll walk you through to make this point. On the left-hand side is a recent comparison we did for 4 container vessels, where we built models of the ships. 2 of them had high-frequency data, 2 of them only had noon reports, and of course, we're able to work with that data and train models. But we looked at a few recent voyages and compared the accuracy to predict speed over ground and main engine fuel consumption. And by averaging out the accuracy across these 4 vessels, we found that the high-frequency data was allowing us to make about 5 times higher prediction accuracy. When you think about the benefit of that, that's the ability to actually identify savings on these voyages and provide trusted recommendations that can help squeeze out those efficiencies. On the right-hand side is a different image. This is actually showing you a plot of shaft power for a vessel. The top time series shows what you would expect from a noon report. There's one average point of power over this 2-day period. It was February 18th to February 20th this year. The plot below that shows the same exact vessel, the same exact metric, shaft power, but it's actually showing it in 15-minute averages. And I want to draw your attention to the 2 highlighted boxes here, which show actually some interesting operating patterns on February 19th into February 20th, which the noon reports just completely miss. You can see there was a point around here, if you can see my mouse, where the vessel was using less power, slowing down. It then got back to a steady state and then gradually accelerated and kept that higher pace throughout February 20th. If you're just using noon report data, you could see all of that information is just lost here. And from a data science perspective, building a model that should predict how the vessel behaves in different conditions, you can see why it's much harder to do with that low frequency data because you're just kind of starved of that information of how the vessel performed and what it was doing in these different operating conditions. The last reason why we feel strongly that high frequency data is the path forward is because it's truly an unbiased source of truth. And this is becoming more and more important to establish, especially as emissions regulations like EU ETS, Fuel EU are having financial penalties. And having very accurate consumption data is critical. Also, MEPC 83 is coming up in a few weeks. We'll see what happens with that. But more and more emissions regulations are requiring collaboration and trusted data in between owners and charterers. And if you look at the images in this slide, on the left-hand side, you can see a very simple high-level diagram of how high-frequency data is transmitted from the vessel to shore. There are really no humans in the loop here when it's operating normally. The sensor signals are being aggregated in a data logger, which is then transmitting that data over satellite collection to different onshore applications. If you contrast that here with the right-hand side, which you can imagine a chief engineer sitting at his computer producing a noon report, there's a lot more room for mistakes and errors in that loop. And as this fuel consumption data is really used with clear financial penalties, it's important to have that unbiased source of data flowing. One analogy that I like to think of here is if you could imagine going to the gas station to fill up your car, and when you put the pump in the car and you start filling up gas, there's no reading for you to see how much gas is flowing into your car or the cost. And then you walk inside the gas station and the attendant says, okay, we did some calculations, we looked at the tank, here's your bill. you could imagine how, not transparent and how that might raise questions for you around what you actually paid or what you tanked in your car. But essentially, that's similar to the workflow of noon reports. Okay, so let's switch gears and talk through some common challenges that we see working with high frequency data from vessels in our pool. Again, I'll talk about three broad buckets here. The first one, actually, Carl mentioned in the introduction. It's simply transmitting the data, so bringing it from the vessel through its network out into other applications. There are kind of two flavors of this. One are physical phenomena, like things like cables getting unplugged on the vessel, or temporary power outages, maybe due to maintenance or other activities, which could cause loss of those signals to any applications that rely on them. The second one is largely a solved problem, but transmitting the data over satellite does have outages. Obviously, this is getting much better with low Earth orbit technology and companies like Starlink, but you can still see that the real-time transmission is a challenge just due to coverage. And to kind of drive home this point, you can look at this screenshot on the slide, which is showing one of the monitoring tools Danelec uses to look at the data being streamed into our cloud. Each row here is a different vessel, and the black portions, or the portions that are yellow or red, are temporary outages where our data packets from the VRS data logger couldn't be sent to our cloud. Now, of course, we're caching and storing that and sending it once we do have connectivity. But this image just helps you show how it's very hard to get real-time signals because of connectivity here. The second bucket of challenges is sensor drift. Where we see this most common is actually in the speed logs. Those can be affected by biofouling because there is a portion of it that is actually flush with the hull, which is exposed to the elements. And at times that could require recalibration or even in harsher conditions, replacing it. The chart here is some real data that we showed from a vessel in our pool. You can see here the darker dots are speed through water coming from the speed log, and the gray dots are speed over ground. And so we're comparing the two metrics over time. And you can see here in this most recent period, February, there's much larger drift between the speed log readings and the speed over ground. And one of the things to note here is that if you don't have a system or a way to constantly check this, you could potentially be using speed data and have that lead to faulty understandings of speed loss. If you're using the speed log to build voyage optimization models, that could lead to predictions that are off and thus missed savings. And so this type of kind of drift is hard to detect unless you have a focus on it or a tool to help you do that. The last bucket of challenges is broadly what we call anomalies with the high frequency data. And there are many variables here. Lots of things can cause this. Again, here, physical phenomena play a role. So vibrations or blockages or even air flowing into fuel flow meters can cause issues here. If you look at the left hand of this slide, this is some data from a container ship that's in our data pool, and they are using a volumetric flow meter specifically on this vessel. And you can see here this outline of, between looks like December and February, there's a lot of erroneous data that is getting transmitted to shore. Our assumption is that this was a blockage in the flow meter. And then you could see actually around February, it's repaired again, and the data looks much better. But again, these temporary anomalies can cause outliers that are not usable for performance analyses. On the right-hand side, there's also an example of draft where we've seen sometimes you could see actually frozen signals coming from a sensor that is malfunctioning. This is an example of plotting draft forward and draft aft from two different sensors from a vessel. And the aft readings you can see here were frozen for a time period, and then that sensor was repaired. And again, we had the normal readings like you would expect. So I'm just showing kind of some common areas where there are challenges with the data. And what I'd like to do now is actually show you a brief demo of a tool that Danelec is investing in to help our clients catch these types of errors and also importantly take action to improve them. So I believe you can all see my screen right now. What you're looking at, oh, cool, thanks, Carl. What you're looking at is an anonymized demo environment of our Fleet Insights platform. This is where our users monitor the technical performance of the vessels. So think speed loss, propeller heaviness, specific fuel oil, charter party monitoring. And we've built this data quality module so that users can, at a glance, see the status of their data and if any action is needed. Right now, there are three main columns here, which I'll describe in this fleet overview page. One is a understanding if the data is actually available. So for the critical tags for performance, like draft, speed, consumption, is that data available or are we seeing an outage? The second column here focuses on outliers. So we have automated outlier detection. So if you think back to the slide I showed with the fuel consumption data, the blockage in the flow meter, we want to be able to automatically detect that and actually filter it from downstream applications. And so there's a high level indication here which shows the amount of outliers our system is detecting. And then this last column here is actually focused on the speed log specifically. As I've mentioned, that's where we do see drift happen frequently. And because speed is the foundation to really any performance analysis, we wanted to create a specialized module and view on the quality of that speed log data. So I'll actually start there and I'll show you what this looks like for vessel 107, where we see the degrading quality of the speed data. So when you start to drill in here, you can see just the overall status. We're telling our users here that there's degrading quality. And the way that we're judging that is through this chart here called historical sensor quality. What we're doing is we're essentially following the difference between what the speed log is measuring and a derived version of speed through water using speed over ground and current data. And so the reason why we can compare those is because they're completely independent from the readings of the speed log. And we have an algorithm which over time is smoothing that data and computing the difference. And what we tend to see is if there's plus or minus 5% deviations, that could be normal noise and difference in these signals. But when we start to see anything above or below that, that's where we would start to alert users about degrading quality. You can see here, starting like in end of December, January for this particular vessel is where we've been detecting poorer quality fuel data. And when I actually just zoom into this time period, I can scroll down here and look at, oh, wow, okay, so here is actually the derived speed through water, and here's the speed log readings, and we can see a much more clear divergence between those two readings for this time period. If I want to zoom out and just see the bigger picture here, it becomes even more clear because you can see for most of this time period, which is almost about a year here, the readings are actually quite close together. But then more recently, this is where the divergence is happening. So that's quite clear. Not all vessels are like this. So, there's other vessels where we see consistently solid quality. So for example, this one was experiencing some diversion that was probably recalibrated. And since May, it's been very smooth. You can see here, there's almost full overlap over these points. And so tools like this, especially when you're managing multiple vessels, really help you get a sense of where there are problems and where not. I'll quickly show you some of the other functionality here. So in addition to looking at the speed log, we have automated outlier detection for speed through water, shaft power, draft, fuel flow. And what we're allowing users to do here is actually configure vessel-specific thresholds so that if anything is out of the reality of the physical bounds of what the vessel or sensor should be doing, that's automatically tracked here. We don't just want to say, hey, there's an outlier. We're also building tools to manage these outliers. Right now, this vessel doesn't have any, but when you do have those outliers, they're listed here, and our users could actually acknowledge or remove them depending on if they believe it's actually an outlier, or if they just say, forget it, keep it in the system and keep it in my calculations. If they do remove it, other parts of our platform that monitor speed loss or fouling, for example, will have that data removed so the calculations are more trusted. And also because, there's a lot of users at some of the companies that work with us, maybe 10, 12 people, we want to have an action log here so that if I remove a data and somebody from my company logs in, they can also see that action and actually undo it if they believed it was a mistake. And then last but not least, I'll just show here quickly data availability. As I mentioned up front, this is looking at the current status of these core signals like shaft power, draft. If the engine has two specific main engines and two shafts, we separate those instead of giving you an aggregate reading. And then if the vessel doesn't have a sensor, like here, we just show an X, so it's not configured. But what this is helping our users do, especially with the fleet overview view here, is at a glance for your vessels, get a quick sense of where I need to take action and where not. So I'm going to jump back to the slides and close out with two things. One is I'd like to show just briefly some future development, which is heading into this module, which I just shared, and then I'll have some key takeaways. So something we're really excited about is actually leveraging machine learning-based outlier detection. So I'll briefly explain what we mean by that. You saw when I demoed the outlier dashboard that we're using physical bounds as our first way to detect outliers. That will capture the majority of them because many of the outliers you can see are well out of the physical bounds of the vessel. But to get the really hard to find ones, we believe that using machine learning models is the best path here. And what I mean by that is we would train a model that takes in shaft power and predicts what fuel consumption would be given that power. And we would actually compare our expected consumption against what the fuel flow meters are producing and flag outliers based on high divergence between those two values over time. So what you're looking at here on this chart, this time series up here where my mouse is, those are actual measures coming from a fuel flow meter. And these orange dots here are the machine learning model actually detecting faulty relationships between power and consumption and flagging those as outliers. The time series below this is just another view here. Here we're looking at the difference between the measured consumption from the flow meter and what the model predicts. You can see that most of the points hover around 0, which is great with some normal noise around 0. But the ones that are much further out here are these orange dots, and that's where we're predicting the outliers. What's helping kind of give us trust in this approach is this image here to the left, and that shows the normal linear relationship between power and fuel. So power is on the x-axis, fuel consumption is on the y-axis. And what we've done here is overlaid the outlier points that the model detected. And you can see here that it's removing some of these more extreme things where it says, for example, at very low 5,000 kilowatts per hour, 140 metric tons of consumption, right? So it's catching these values which show a big divergence. And this is something that the data science team here at Danelec is working on right now, and we're planning to bring into the outlier detection of that product that I showed you. Great. Okay, so let's close up before we get to questions on just a few key takeaways. There are 3 points that I'd love to leave everybody with. One, I'd like to reiterate that high frequency data is the way forward. The reasons we talked about is that there are simply some things that you can't improve if you can't measure it. There are some use cases that require this granularity to save fuel. The second is the higher prediction accuracy to squeeze out fuel savings on voyages. And the third is that it's an unbiased source of truth, which is becoming more and more important with the emissions regulations that have financial consequences. The second key takeaway is that high-frequency data does have some unique challenges, especially when you're compared to using noon reports. Things like transmission challenges, drifts, anomalies that we talked about, and those do require your system to have some specialized monitoring like we've built to do that. The last key takeaway is that Danelec is really a premier partner for high-frequency data, whether it's collecting or actually monitoring the quality of that data. We do have end-to-end expertise in not only generating that data through our power meter, but collecting it, transmitting it, and then correcting it, and finally analyzing it for our downstream products like voyage optimization or performance monitoring. So that end-to-end expertise in-house has helped us think through and work on this problem. Great. I thank everybody for their attention. I'll pass it back to Carl.
Well, thank you very much, Conrad. So we're going to the Q&A section. So we're open to questions now. I can see 2 complicated technical questions in there from Julio. Maybe we'll start with one Well, I was thinking more generally. So one thing I've noticed from our webinars is every shipping company seems to be having enormous difficulty with getting data from ships, because we get questions in every single webinar. What's the best way to get data from ships? And I suppose it's an incredibly hard problem, but I guess we're seeing what the solution looks like here. You probably do need some kind of a service provider like Danelec that will do the hard work of gathering all this stuff together. And then for a performance manager, you want to log in once a day and skim through your dashboard there and see if anything needs to be done. This probably where we're going, isn't it? I think it's
Yeah, no, I mean, I think that's a fair way to describe it. One thing is that every vessel is a project, right? To map out what are the systems on that vessel, what sensors are already available, what are not, what is the manufacturer of the IIS system, what's the manual of that IIS system to see how the tags are created. All of this requires some expertise and knowledge about how to work with these onboard signals and ultimately get high value data from it.
yeah, very good. So well, we can go to Giulio Gennaro works with floating nuclear power, according to his LinkedIn. I know you're not an engineer, so maybe you don't know. Well, he's asking first, how is thrust measured by the device? I think when you're not measuring thrust directly, you're measuring torque, and you can infer the thrust from that if you've got a model of the propeller. Is that
Yeah, so our shaft power meters have an additional kit which can be installed to also collect the thrust data from the vessel. The exact technical particulars of that, I'd love to connect you with some of our team that manufactures it. But what I will say is that the out-of-the-box version focuses on torque, and then there's an additional add-on which we can fit to also capture the thrust movements.
Oh, very good. And then another complicated technical question from Giulio about noon reports being a long time average, not actually low frequency data. I'm not sure. I mean, I was thinking about this. I was doing some Googling when you were talking. I'm not totally sure there's difference between when low frequency data means you get a data point at low frequencies. I mean, I can guess you can either have a snapshot or you can have a summary of do you think there's an important differentiation there? So
No, I mean, I think it's a fair question. There's really no standardized way to produce noon reports. I think Julio raises a good point. We've seen some vessels do averages of the data over the period of the noon report. Some actually report in that real time when they're producing the report. What is the power of the vessel, for example, at that point? I know that there are some bodies that have attempted to create a standardized noon report, like LEAP, I believe, is one of them. But yeah, there's challenges there. You have to really understand what the methodology is for the crew to generate the data. I think the point that I was trying to make in the slide that showed the power over time is that regardless of how you're reporting the noon data, you're missing a lot of the actual granularity of what's happening within that reporting period. And that granularity is really important to build a model that can predict anything. And so you can definitely build noon report digital twins. That we've done that. We've been doing that for years. It just requires a bit more data because you lose a lot of the granularity of what's happening.
oh, very good. So bit obscure. Oladeyi Sadiq asking if Danelec has an office in Nigeria.
I don't believe we do, but one of our partners that I mentioned might be operating there. So I can get your contact information from this chat and connect you with our local partner who operates there.
Okay, so Victor Colazos, who's a decarbonization manager with V Group in Monte Carlo, is asking about your opinion of synthetic data and how it can help in the future to share data of vessels. I don't think you showed any synthetic data unless you're talking about if you're using it to fill the gaps between when you don't have sensor data. I mean, I'm not
Yeah,
sure.
no, I'm curious. Yeah, I'm curious about the definition of synthetic data here. It's funny. My mind first went to what's happening with large language models and creating synthetic data to train them because they're running out of training data. But I think it's probably more about supplementing the high frequency data with, let's say, with other sources. Um, that's something that I know our data science team is really interested in, is to kind of produce like a best measurement with all of the various types of data that we could collect. Um, but I think there is room here. I think there's an interesting opportunity to actually look ahead and say, how can we amalgamate different sources and create a best-in-class measurement? And we've actually called that internally virtual sensors. So if you're interested in collaborating or learning about that, happy to share more.
Yeah, I mean, it's not data completely made up by machine. It's data derived from other sensors. So I guess you can have a virtual shaft power meter using data from the fuel meter. I guess as long as you know what you're dealing with, I guess might be useful in certain circumstances, I suppose, isn't it?
Yeah, it's a hard problem, but sometimes you can arrive at better measurements by using multiple sources and trying to infer what the best value is.
Very good. So Christian Bjerke, who's Vice President Business Development with Nortec in Norway. How long do you estimate a project mapping out a vessel will take? I'm not sure what you mean by, because I mean, I guess it's very different stages of this. I mean, installing sensors is one stage and sending the data to shore, and then I guess perhaps he's mapping out a vessel, thinking building the model of what good and bad looks like. I suppose that's what perhaps he's referring to, isn't it?
Yeah, no, I agree. I think there are many stages to the project. It helps if we're working across multiple sister vessels that have very similar arrangements and equipment on board. But I guess it depends on which part of the project you're thinking, whether it's more about installing the sensors and the hardware or actually collecting them in a data logger and sending that data or building the digital twin. We kind of have expertise in all of those stages, but I guess the timeline depends on um, which stage we're working in.
Oh, very good. So this next question is about your modeling. So Mudasir Wagler. So he's Senior Vessel Performance Manager with Oldendorf in the Middle East. How do you derive predicted fuel consumption accurately because condition of the fuel system is not always known? I'm not sure because if you've got a flow meter, you know the fuel consumption accurately. I don't know why you'd be. Perhaps I missed. Do you know why he's?
Yeah, no, I think that's a good question. I mean, you might be referring to the different qualities of fuel that can sometimes change the actual energy that's available to the engine and the efficiency. Um, that might be what your question is. And if that's the direction, wherever we do have the actual lower heating value and the quality of the fuel in our data, we use that to correct and normalize the fuel consumption. So for example, our onboard system actually allows the crew to enter in the lower heating value of the fuel and the density after they bunker, and we can take those and then normalize the fuel consumption. So I'm not sure if that was where you were referring about the fuel system, but that is an important input for us when we model consumption. But broadly, the way that we build our models is more of like a gray box approach, which means that we have a formula based on naval architecture first principles that predict the fuel consumption given inputs like speed and power, currents, wave height, wind. And we allow the model to look at all of the vessel's history and then understand what the exact formula will be based on that vessel's actual data. So it's not this black box, we don't know how it works sort of machine learning. It's constrained using naval architecture first principles and the actual data, historical data from the vessel.
Yeah, you're also looking for things that change. So I guess if the fuel consumption pattern with the flow meter is sorry, the flow meter pattern with the torque will follow certain patterns, and if that changes, this indicates something wrong with the sensors. I guess that's also with on the
That's
data
right.
quality.
That's right. There's kind of two ways we do that. One is what you just said, which is we monitor the actual quality of the data coming in. And our digital twins are actually retrained weekly so that if there is difference in performances, or let's say a retrofit or something changed significantly, the model can pick that up. And so it's not using stale data.
Okay, so Jofi Wang, who's a digital development manager with McGregor's, asking how she can get in contact with you. I don't know if you're happy to share your email address with people or.
Yeah, definitely. It's kge@danelec.com. So anybody here, just feel free to email me. And if it's not myself that can help, I'm happy to point you in the right direction. I don't know if we can put that in the chat. Maybe
Yep. KGE at no,
danelec.com.
yeah, we'll share it with other people afterwards, I think.
Great.
So Peter Lee is with Oldendorf in Germany. I don't quite understand this question. Maybe you do. So derived speed through water is reliable. The current effect on the ship is also high frequency. I don't remember you talking about derived speed through water. You were talking
Yes,
about.
I talked about derived through water
Oh,
as
right,
a
okay.
tool, as a yeah, it was fast. It was in relation to the speed log module in the data quality product, where we use that to identify if speed logs are faulty by comparing the speed log and the derived speed through water over time. And that question might be about that there could be bias or that the current data is not reliable. Do you mind repeating it? I missed
Well, you derived speed through water is reliable. The current effect on ship is also high frequency.
Okay, that is probably a great question for our data science team that is working with this much closer, and I'm happy to take your contact information and provide more details on that.
Okay, so now we're going to France. Chloe Papola, data scientist with Sirocco, is asking about the impact of weather data. I mean, weather data is not part of sensor data. I don't think you're getting involved in weather data. Would
We
you be
do.
able to? Oh, okay.
Yeah, that's a great question. So there are a few different ways that we work with weather data. One is using the actual weather station on the vessel itself, if that data is available. We do find, though, that it is at times not the most reliable source of actually the current weather conditions that the vessel is facing. And so we tend to like to rely on other third-party sources that have A, higher coverage of the globe and of the oceans, and B, more data points like sea surface temperature, salinity for us to use in both training models and also just displaying in our applications so that the data is in context of the actual weather. But that is a great question. Like weather data tags are critical for performance and modeling.
Yeah, she's got another question. Can you evaluate the quality of weather data with the?
Mhm. That's harder. That's a great question. I think that's harder because it's there's not a lot of independent sources. You know, what you could do is, and we've done these types of analyses, is actually compare the third-party sources to the weather station on the vessel to identify bias or incorrect data. But I think it's a really hard problem to be able to systematically look at the quality of the weather data. It's something, though, that I know our data science team has thought a lot about.
Oh, very good. So now we're going back to Norway. So Andreas Meervold, who's a performance analyst with Hogue EV. So he's asking about outliers. What's your typical approach to filter them out? Is each data point flagged as a non-outlier or outlier and then filtered, or other approaches?
Yeah, no, that's a great question. So once the system detects that a data point is an outlier, we flag it and allow a user to either acknowledge it, which means it's okay, it's not an outlier, or remove it. And removing it actually removes that data from being used in speed loss calculations or specific fuel rate. And so what the system does is it removes the entire calculation for that timestamp so that we're not incorrectly filtering out speed, but using power and generating a false KPI for speed loss. We just take the actual timestamp for the when the outlier was detected and don't use that in the actual calculation. So we take the approach to ensure that we're not just kind of plucking data out without looking at the wider context of how it's used in the calculation.
Yeah, yeah. I was studying chemical engineering, and we had a laboratory project, and the data we got didn't make sense. So we went to the lecturer and we said, this data doesn't make sense. And he said, well, just scrub it out, which spent the last 20 years wondering if that was the right answer or not. But I guess you need to have expertise to know if
I
it's good
like
or
that.
not, which is kind of what you're saying, isn't it? Yeah.
Yeah, yeah.
Oh, very good. So we've got a question, maybe better offline. So Olade from Nigeria is asking what he needs to do to get in contact to be a Danelec partner. Perhaps that's I guess not a discussion to have in public. So perhaps we'll
Yeah, you
have
can
a.
shoot an email. If we'll drop my email and then I'll connect you to the right person.
Okay, another question about water monitoring systems. I think this is probably a bit out of scope, but perhaps we'll take that one offline, I think. So we're going back to Christian Burke, who's or Burker from Nortec. To clarify, I wanted to understand the first phrase. Were you to map out what you have to do to get the first data stream? How long does this part of the project take? So to get the first lot of data, I mean, I would have thought if companies have sensors, they've got a data stream just by installing them, haven't they? Or just you?
Yeah, he might be asking about, assuming the vessel doesn't have any sensors and we need to install a power meter and or fuel flow meters need to be fitted. If in that case it would take longer because that would sometimes require a dry dock, especially with flow meters, if the pipes need to be cut. And for our shaft power meters, we do fit them custom for the actual diameter and measurements of the shaft. So that does take a longer time than assuming if the vessel already has all the sensors equipped, and it's more of an exercise of reading documentation, understanding the different types of signal, Modbus, pulse, whatever the signals are, and actually collecting those in the VRS data logger. That's obviously a much faster project. Could take a few weeks, depending on the availability of the documentation and the vessel schedule, because we would need to bring somebody on to do the cabling and the connections. But it really just depends on the kind of status of what is already on the vessel and what not. And that's why each vessel is kind of a project that we can help manage.
Wow, very good. So we've got a question from Jutta Blom with an acronym I don't know. I understand you use the RDI. Do you know what RDI?
That's a conversion kit
Oh.
that converts different types of signals to the VRS data logger. So depending on the signals that we need to collect on the vessel, we may need one of these RDI conversion kits to collect the data.
Okay, so the full question, I understand you use this data conversion kit to collect data from a sensor. Why do you need a Kyma system? But the Kyma system's a sensor itself, I think, isn't it?
The Kyma system is a power meter. Yes, so
Yeah.
it's a ring fitted on the shaft, and that data is just one piece of what the data logger could collect. There's also other data. I think the question is about why we need both, or could you reread it? I didn't
Yeah, I don't quite follow what, yeah. Why do you need a Kyma system if you also have a RDI system? But a Kyma system is a sensor itself, isn't it? So maybe some misunderstanding.
Yeah, no, I think that might be a good question for the Kyma team. But it's the short answer I would say is that it's just a very different device. We're using a power meter. It's a sensor to generate the torque measurements. But if I misunderstand the question, happy to connect offline and provide an answer.
Oh, very good. So just go back to the big picture then here. So I guess it's pretty clear every company will need this. Every company is going to need high frequency data because the demand for data are going up. And every company will probably need a service to manage it because it doesn't manage itself and a lot of things go wrong because these sensors are very complicated equipment. So I guess this is the kind of level that every company should be thinking about. I mean, it's not like you have to use Danelec. There's other services around that do this, but something or other, I guess every company would need to do. This is how you probably
Yeah,
where we're going. And
yeah, I think a nice shorthand way to express that is leveling up your data capabilities in your company as you're leveling up the technology on the vessel. So just adding the sensors and the technology and ignoring the tools to monitor the data and correct it, it's better results when you level up both in tandem at the same time.
oh, very good. So we're going back to Monaco now. So Victor from V Group, does your accuracy model get more accurate over time? Do you retrofit based on historical data your model? I think by the accuracy model, perhaps he means the model of knowing if the sensors are working or not. So I guess yes, it would, wouldn't it? Or is that more data
It
you put in?
does. Yes, and that's the benefit of using a machine learning approach, because when you're retraining and you have more data, the model sees different conditions that it may not have seen in other historical data. And so it's doing less inferring or less stretchier inferring. So yes, the models do definitely improve over time.
Yeah, very good. How is the interface with the shipping company performance works? I mean, you didn't show any alerting, but presumably it's got some of that in it as well, or they don't have to log on every day and look at this, do they?
Yes, yeah. So there's an automated email alerts that our users can set up. So to your point, if they don't want to log in, they can just wait if an email happens. Let's say if there's a data quality issue that we've detected. We do have some users who we see are very, very hands-on. They're in there every day making changes, and others who are more passive. So it just depends on your working style.
So there's another layer of expertise of knowing what to do when something goes wrong, I suppose, or knowing how important something is, or if you've got to.
Yeah, I mean, a lot of the first steps are simply contacting the vessel and understanding, eliminating some of the easy ones. Our team has a pretty simple checklist, like, is the box unplugged? Is the specific cable unplugged? Like, getting rid of some of those very easy questions. And then it might be a networking issue. It might be something wrong with the sensor itself. So there's kind of a process of elimination.
Oh, fantastic! Yeah, I think we can see where we're going. Well, we don't have any more questions, so I don't know if you want to give a couple of minutes to sum up and say anything you want to leave the people with. But I mean, I guess the main thing is if you get the message about wanting better data from ships, Danelec's good people to talk to, I suppose. That's a sort of...
Yep, that's a solid message. And I just want to thank everybody for joining and the questions. I know that there were a few that require some follow-up, so please don't hesitate to reach out to me. It's kge@danelec.com. And yeah, we're looking forward to partnering with you on your data.
Yeah, well, that's great.